All right, so here's our lecture on linear interpolation and linear regression. This is a follow-up to the statistics lecture when we talked about there were summary statistics and there were inferential statistics. So the two inferential methodologies that we'll discuss in this class are linear interpolation and linear regression. They have different uses, so we're going to discuss the difference between the two, and then we're going to get into the meat and potatoes of how to use each one. So let me go ahead and bounce to my next slide. So we're going to start with the idea that, look, so if I told you that summary statistics were where we had a whole plethora of data and we wanted to distill down a set of numbers that would explain that mass of data in a smaller subset of numbers. So instead of looking at a billion numbers, we could have the mean, which is one number, which gives me a measure of the central tendency of all those billions of numbers. We talked about the center of mass. I told you that at some point we'd be using those values and playing them forward to make estimates of future values. This is that time. So we're not going to use all of the summary statistics. We're just going to use one, actually. But we are going to learn some methodologies for approximating or estimating a future value given past occurrences. So first, we need to have some excuse me. We need to have some data. Second, we need to understand that sometimes our data is well organized, sometimes it isn't. Sometimes we can assume that a missing value, or the value that we want, lies on a line that connects 2 points. Sometimes the data is just completely random. If we were to plot it, it would be scattershot all over the board and we wouldn't be able to find any clear trend or pattern to it. And so we would need to plot a theoretical relationship and use that theoretical relationship to predict future outcomes. So the first method, where we can connect points, that's actually linear interpolation. So if we see an apparent trend in our data, we're going to use linear interpolation. If there's no trend, again, if it's scattershot, then we're going to use linear regression. So let's start with linear interpolation. If the data exhibits a clear pattern. Now, it doesn't have to be any single pattern. So this is a straight line, right? So if we were looking for data between any of those 2 points, we could connect them with a line. This is a sort of sinusoidal curve or an exponential trend. Here's another exponential trend, and here we are. So all of these have an apparent trend, right? Mathematically, it looks like we can connect points and approximate anything in between these occurrences. Now, remember I told you when we were doing rules of proper plots that when you had empirical or observational or experimental data, that those were discrete points. So here we have some discrete occurrences. We would plot them, and then if we wanted to estimate, or if we wanted to predict a value that was not measured in that discrete data set, then we could connect 2 of those points, and we could use the line that connects those 2 as a way of approximating everything in between the 2 points. Now, here's how that works. So, all right, let's say we have some data. Okay, let's say given some x value at this point where I've put my green hash, I need to estimate or compute a value of y. Well, first I have to understand that that green tick is between these 2 points. I'm going to call them point 1 and point 2. Then I'm going to understand that that's point 1 and point 2. I'm going to call this x3. That point 1 has an x value and a y value. Point 2 has an x value and a y value. Similarly, point 3 has a y value, but that's what we're going to estimate. That's the unknown. So what I'm going to do is I'm going to connect points 1 and 2 with a straight line. Once I do that, I can place a dot on that straight line, and that's going to have the x and y coordinates of x3 and my predicted y value. I'm going to call that point 3, and there we go, there's my y3. This is what we're going to focus on, all right, this methodology. Let's blow this up, all right? I have point 1, I have point 2, and I have point 3 in the middle. If I make a right triangle out of points 1 and 2, and I make a right triangle with point 3, and I put the x values up, and I put the y values up, then now what I actually have are 2 similar triangles. And similar triangles have the same ratios, same proportions, same slopes. I'm going to center off of slopes. You can do ratios, you can do proportions, but my favorite is to do slopes. So here's what we're going to do. We're going to do the slope of the bigger triangle, y2 minus y1, over x2 minus x1. That equals the slope of the smaller triangle, so y3 minus y1 over x3 minus x1. We rearrange the whole thing for y3 because, again, given that image, or that the plot where we showed the x data and the y data, y3 was our unknown. So let's put that all by itself. So y3 equals y1 plus x3 minus x1 times y2 minus y1 over x2 minus x1. All right, So this is going to be our equation. y3 equals y1 plus x3 minus x1 times y2 minus y1 over x2 minus x1. Let's take a look at where we can use this, all right? Principally, where a lot of you are going to bump into this is thermodynamics. So in thermodynamics, you're going to use steam tables. You're going to do a lot of linear interpolation. Unfortunately, at our university, they basically expect you to understand how to do linear interpolation before you get there, so they don't actually show you how to do it. So yeah, good luck. But you can always revisit this. This will be up for a little while. So here we go. But I'm going to have to give you a background. So here, you can stop and read this, but I'm just going to brush over it. There's a document in the United States that governs how we build buildings. It's called ASCE 7. Now, it goes from years, so like 702, 705, 710, whatever. It's based on the year it was released. But it has in it a provision for how to design buildings for wind. Now, that's complex, but we're going to distill it down to a simple we're going to distill out a simple portion of that process to use in this example. So here, we're designing a building for wind speeds. There's the equation up top. The wind speed at some height equals the wind speed at 10 meters times some multiplier. See, here's the thing. We can't keep a record of wind speeds at all elevations all over the United States. So the way that ASCE 7 does this is they keep a map of wind speeds at 10 meters. And then they say, look, depending upon the height of your building, because your building could be a house, or your building could be like the Sears Tower in Chicago, which was in the background of some of the videos at the beginning of the class. Depending upon that, and to me it's the Sears Tower, I don't really care what anybody else says. So your building could be a house, or your building could be the Sears Tower. We want to design, or we're going to have to design elements on both of those buildings for the max height. Now, obviously, the max height of the house is far less than the max height of the Sears Tower. Therefore, our wind speed that we would use to design the top of the Sears Tower is much higher than the wind speed we would use to design the elements at the top of the house. So, wind speed increases with height. That's why. The higher the wind speeds, the higher the loads. We're not going to get into the equation. We're just going to say the higher the wind speeds, the higher the loads. And if you were to map wind speeds from the ground all the way up to the atmosphere, it would look like this. This is called a boundary layer. If you ever hear that when they're talking about tornadoes and hurricanes, the Weather Channel, when they send their really pretty people out in the middle of bad weather to stand there for some stupid reason. This is something that they might show you, but we use this in design all of the time. It's how we design buildings to withstand wind. So if the wind speed increases with height, and I told you that equation up there was the wind speed at some height equals the wind speed at 10 meters times a multiplier, and what we need to understand is what are the multipliers? Well, the multipliers come to us in a tabular form, like this. This is going to be where our interpolation comes from. This whole phenomenon is predicated on the idea that, and I didn't add it, I apologize, there's supposed to be a red line at 33 feet, but that's fine. It's predicated on the idea that the wind speed at 10 meters, or 33 feet, for those of you schooled in the US and you don't know what a meter is, that the wind speed at 33 feet equals the wind speed at 33 feet times 1. So we're going to prove that. All right, so here we go. So I want to find the KZ factor from this table at 33 feet. I have a KZ factor at 30, I have a KZ factor at 40, but I don't have one at 33. So let's go ahead and compute it. The first thing I'm going to do is I'm going to box the information. Now, I'm going to tell you that right now, I'm just going to stop. Some of you think that drawing the box around that information is cheesy, corny, whatever. Pedantic, sophomoric, I don't care what adjective you use or adverb. But the thing is that cognitively we've drawn a fence. We've focused on the information that we need, and we've excluded everything else. So, right, the forest for the trees. And it is important to note that in thermodynamics, if you're using this methodology with steam tables, a steam table sheet, it's not 2 columns. It's like 12. And it's not 10 or 15 rows, it's like 40. So if you circle the information, or if you better pull it out and rewrite the 2 pieces of information that you need, x and y, then you can use that instead of focusing on the entire table to move forward. Right? Anytime you can exclude all of the noise to focus on what you care about, it's just important. So I will tell you that when I use linear interpolation and I go to a table and I have to do this, I do it exactly like that. I draw the fence. Here we go. Now we have to have a 0.1 and a 0.2, right? So we're going to call the top one 0.1. So it has an x1 and a y1. We're going to call the bottom pair 0.2, an x2 and a y2. We know that we're looking for an x3 at 33 feet. I'm sorry, we're looking for the y3 associated with an x3 at 33 feet. And in our terms, for our theoretical example, that's the kz value at 33 feet. So a y3 or a kz at 33 feet, it's going to be somewhere in here. Now, intuitively, we should understand that because we're connecting 0.98 and 1.04 with a straight line, the output or the end result of our calculation needs to be between 0.98 and 1.04. So let's go ahead and start filling some stuff out. So we said that we needed y2 minus y1. So I'm going to take 1.04 minus 0.98. That was going to be over x2 minus x1. So that's over 40 minus 30. Good, so that's half, right? That's the big triangle. Now the little triangle. That equals y3, that's my unknown, minus y1, 0.98, over x3, 33 feet, minus x1, 30. I need to rearrange the whole thing for y3 again, right? So y3 equals that 0.98 plus my 33 minus 30 time cross multiplied into the numerator, so multiplied by the quantity 1.04 times minus 0.98. All divided by 40 minus 30. When I work this out, it equals 0.998. Now, that's roughly 1, right? It's within the margin of error. All of the numbers that we had were 2 decimal places. 0.998 rounded to the 2 decimal places is going to be 1. Okay, so if we use the right number of significant digits, that's what we get out. Remember, this entire phenomenon was predicated on the idea that v at 10 meters, and I told you for those schooled in the US, v at 33 feet, it equals a k factor at 33 feet times the velocity at 33 feet. So the velocity at 33 feet actually equals 1 times the velocity at 33 feet, which is what we were talking about, given that figure, right? We can't keep a standardized table if we have to keep track of infinite wind speeds from 0 to 1,000 meters all over the US. So we just keep track of 10-meter wind speeds. And with this table, we can then multiply them to get the value that we need to use to design a building. It's actually very simple. The nuance of it, it goes way beyond that. It's a little more complicated, but this is how we get the wind speed. Okay, so let's go through another one. We'll clear our work, we'll clear the figure. Let's go after 55 feet, because what I actually want to show you is this. Again, I'm going to draw my cognitive fence, but instead of 0.1 being the top values, or top set of values, now x1 is going to be my bottom set of values. So 55 is between 50 and 60. That's why my fence goes around the 50 and 60 information in the z column. So 1.09 and 1.13 in the k column. My second set is going to be my x1, y1. My first set, 50 and 1.09, that's my x2, y2. I'm looking for a kz at 55 feet, so that's my x3, 55, and knowing that somewhere in there between 1.09 and 1.13 is going to reside my kz at 55 feet or my y3. Again, we're just going to throw it all up there. I have y2 minus y1, okay, so 1.09 minus 1.13 over my x2 minus x1, 50 minus 60. That equals my y3 minus y1, my unknown minus 1.13, over my x3 minus x1, which is 55 minus 60. Rearranging for y3, we get 1.13 plus that cross-multiplied 55 minus 60 up into the numerator of the opposite side, so multiply by 1.09 minus 1.13, divided by 50 minus 60. Which equals 1.11, which intuitively makes sense, right? 55 is halfway between 50 and 60. 1.11 is halfway between 1.09 and 1.13. That's also an important step. When you finish doing a linear interpolation calculation, you should make sure the value that you computed is between your y1 and y2. Because in theory, we're connecting 2 points with a straight line. The value you compute has to be between those 2 values. So just run that check in your mind. All right, so let's move on to the other one. So we said that, look, if there was an apparent trend to our data where you're going to use linear interpolation, I showed you graphically how it worked, then I did a tabular or a numeric example. Linear regression, however, it's not as theoretically hard to grasp, but it is computationally a little more involved. So let's just go ahead and get started. So let's say I have some scattershot data. What I want to do is plot a line through that data, and I'm going to say that, look, any predicted value of y given a value of x is going to be on what historically most of you have called a line of best fit, right? So we're going to fit a line of best fit to this data, and lucky for us, the only thing we're going to do in this class is first order linear regression. So our line of best fit is going to be in the y equals mx plus b category. Now you'll notice the text is getting smaller. That's on purpose. I know that when some of you watch these videos, you have them set off to the side. I don't know what else you're doing. I don't know if it's Netflix or It's not Facebook. Shit, I don't know. I don't know what it is, okay? But now you're going to have to pay attention and blow this up because the text is going to get even smaller. I told you that the equations are a little more nuanced, they're a little more involved, so let's just get into it. So this is in the y equals mx plus b paradigm. However, going forward, I don't want you to think of a first order linear equation as y equals mx plus b. In this class, we've already talked about matrices. I had a coefficient matrix, and I have an unknowns matrix, and I multiply them together, and one is a column, the other is a row. I can get a linear expression, and that's what linear equations gives me. So I told you that a lot of students at our university choose to get a math minor. To do that, they take linear algebra. If you're going to do that, do it early, not late, because it's going to better serve your academic career. So that means that instead of y equals mx plus b, I want to look at this as y equals a1x plus a naught, which is actually a1 times x to the 1 plus a naught times x to the naught. And x to the 0 is just 1. So I have a1 times x to the 1 plus a naught times x to the naught. Well, let's attack the slope, the a1 term, right? So a1 is going to equal this. Now, again, I want you to put into your mind that I have a set of data, right? Those points. They have x values, they have y values. So what I'm going to do is, I'm going to say that a1, or the slope, equals the number of points I have. I'm going to multiply that by the summation of each x term multiplied by its y component. So, right, each ordered pair has an x and a y component. We're going to multiply that together. Then we're going to sum up all of those products. We're going to subtract from that the summation of all the x terms times the summation of all the y terms. All right, that's my numerator. In my denominator, I have, again, n, my number of points, times the summation of the xi terms squared. Now, this is an important distinction, but I'm going to finish the equation before I get there. Minus the summation of the xi terms quantity squared. Here's the deal. I want you to focus on the bottom two. They're not the same. The first one is where I take each x term, I square it, and then I sum up all those squares. The second one is where I sum up all the x values, and I take that summation value, then I square it. Those are different. You will find that summation of all of the x values in the numerator and the denominator. So the first mistake that a lot of students make is they assume that those two summations in the denominator are the same. They're not. The second assumption that some students make improperly is that they can factor out the n's. This isn't one of those things that for shits and giggles we just threw n's in mathematically like 200 years ago. They don't distribute across the whole numerator and the whole denominator. It's n times the first term in the numerator, and it's n times the first term in the denominator. It's not n times the whole numerator and n times the whole denominator. So please don't factor out the n's, and please be aware of the difference between the summation of xi terms and then that summation value squared, and then where we square each x term and we sum up the squares of the terms. Well, again, let's put some numbers to this game, right? Oh, sorry, we need the y-intercept. I always forget to do that, I'm sorry. So the y-intercept, or a naught in our parlance here, is going to equal the mean of the y values minus our a1 value that we compute times the mean of the x values. Well, that equals the summation of all of the y values divided by the number of values, or the number of points we have, minus our a1 value that we compute times the summation of the x values divided by the number of points we have. So let's put some numbers to this game and run through a quick example. So here I have an x data set and a y data set. Theoretically, we're not going to give them values. We're not going to say speed versus time or pressure versus time or whatever. Okay, we're just going to say, or force versus pressure. What we're just going to do is we're going to say, look, I've got x values from 1 to 7. I've got y values of 0.5, 2.5, 2.4, 3.5, 6, and 5.5. I'm going to find the theoretical relationship between the x and y values. And also I want to predict or estimate a value of y for an x value equal to 5.25. So I'm going to create the theoretical relationship, then I'm going to exercise it a little bit. I'm going to give myself a value. Well, the first thing I'm going to do is I'm going to make a table. You guys at this point know I like tables. Okay, they're straightforward. From an algorithm standpoint, it's easy to follow, right? Step by step, left to right, up to down. There we go. So I'm going to multiply my x and my y terms in the first row to get my xy term for the first row. 1 times 0.5 gives me 0.5. For my second row, 2 times 2.5 gets me 5. 3 times 2 gets me 6. 4 times 4 to 16. 5 times 3.5 gives me 17.5. 6 times 6 to 36. And 7 times 5.5 to 38.5. For the last column in this table, I'm just going to square all the x values. Now I have counting integers, right? So let's just square up the counting integers. 1, 4, 9, 16, 25, 36, and 49. Now I need to sum all of those up, right? Because in the equations, I have the summation of xi terms, the summation of yi terms, the summation of xi yi, and the summation of xi terms independently squared. So I'm going to give myself some locations to do this. The summation of the xi terms is 28. Summation of the yi terms, 24. Summation of xi yi, 119.5. And then the summation of the xi terms independently squared is 140. I'm going to collect all my information. All right, now a lot of you don't do this, that's fine, but I'm going to. I have 7 points. My summation of xi terms is 28, my summation of yi is 24. My summation of xi yi is 119.5, and my summation of xi terms independently squared is 140. So I'm going to put in all the values that I need, or all the information that I need to compute my slope. A1 equals n, 7, times the summation of xi yi, 119.5, minus the summation of my xi, 28, times the summation of my yi, 24. All that divided by n times the summation of xi terms independently squared, so 140, minus the summation of xi terms squared. So again, I made the point that I wanted you to look at the distinction between the summation of the xi terms independently squared and the summation of xi terms quantity squared. Look at that, okay? That equals 0.839. We're just going to do it down to 3 decimal places. That's just what we're going to do to roll. Now we're going to compute the y-intercept. So A naught, it equals the summation of my yi terms divided by the number of elements, 7. Okay, that's the mean of the y data set. Minus the A1 that I just computed, 0.839, multiplied by x bar, which is the summation of xi terms, 28, divided by the number of points n, 7. And with that, I get a value of 0.07, which means the theoretical relationship is y equals 0.839 times x plus 0.07. Now I'm going to use that. I want to know what's an estimated value of y given a value of x at 5.25 that would lie on that line of best fit. Over there on the left, you can see that red line, right? So I'm going to substitute it in, which means that my f of x notation, f of x equals 5.25, or y at 5.25, equals my slope, 0.839, times my value, 5.25, plus 0.07, or 4.4747. So that's it. Now, if we have data, we can look at it by plotting it. We can figure out, look, is there a clear trend to it? If there is, then we can use linear interpolation. And we can estimate a value in between known quantities. If it's not well organized, it's just scattershot, there's randomness to it, we can fit a line of best fit, and we can use that to estimate or predict future values given some value that we're looking for or interested in. In this class, again, we're going to focus on first order, so you don't have to go beyond that. This won't be sinusoidal, exponential, logarithmic, nothing like that.